Good morning, everyone. Hope I'm audible. Esteemed resource persons, respected participants, on behalf of the Department of Mathematics, Maristella College, Vijayawada, I render a warm welcome to each one of you. This is a two-day national webinar on real analysis. The topics to be covered in this webinar are sequences and series, limits and continuity, and differentiability. The core idea behind the conceptualization of this webinar was to address the concerns of the student community and fresh faculty who may find it challenging to explain these concepts. To clear such apprehensions, our honorable resource persons have adopted an interactive approach in their lectures. Hence, we inform all the participants that we have selected for this reason only the basic concepts in real analysis and will be exploring them in detail. Now, let's start the formal proceedings of the day. It's now time to seek the divine blessings of the Almighty for the smooth conduct of this program. I now invite Sister Balasri and Sister Nirupama to render the prayer song. Sister, over to you. Sister Bala?
Yes, ma'am.
Yeah.
Ma
Thank you, Sister Balastri and Sister Nirupama, for that soulful rendition. A strong and supportive management is the backbone of any organization. It's because of them that many of the ideas developed at the departmental level get materialized and deliverable. It's my privilege now to invite Dr. Sister Inyasamma, Degree Vice Principal, to give her welcome remarks. Sister, please.
Thank you, Sudha. A very good morning to all. On behalf of the management, staff and students of Maristella, it's my great privilege and honor to extend a very warm welcome to our eminent resource persons, Dr. R.Vembu, Associate Professor, Professor R.Roopkumar, Head Department of Mathematics, Central University of Tamil Nadu, and Dr. C.Ganesan, Assistant Professor, for this two-day national webinar on real analysis. We are grateful to all of you who are present today and those who are going to join tomorrow for taking time out to be with us and share your expertise. I am pleased to welcome the faculty and students from other institutions. I congratulate and thank Mrs. G. Usha Kumari and Mrs. V. Sudha Devi, HODs of UG and PG, and all the staff and students of Mathematics Department who made their utmost efforts preparing this webinar. I wish you every success and hope this two-day webinar will be the opportunity for the participants to leap forward and demonstrate skills learned. I hope all of you to have successful results. Thank you.
Thank you, Sister, for your warm and endearing words of welcome. Now, Mrs. G. Usha Kumari, Convener and Head Department of Mathematics, will give her opening remarks. Over to you, ma'am.
Presentation. Screen. Good morning to one and all. Respected resource persons, distinguished participants and students. It is a glorious moment to extend a warm welcome on behalf of the Department of Mathematics, PG and UG, Maristella College, Vijayawada, for this two-day national webinar on real analysis. Real analysis is typically the first course in pure math curriculum, as it serves to introduce the important ideas and methodologies of pure math in the context of already familiar material. This webinar, however, attempts a different approach to these topics with the objective of imparting a clearer understanding of the concepts. It is envisaged that this new approach will be particular use to fresh faculty who may find it challenging to explain these concepts. Clearly, this webinar schedule brushes upon a spectrum of exciting and befitting theorems that discuss the geometrical perspective and logical proof. I very much believe that anyone can learn anything as long as it is explained clearly enough. I want to convey my heartfelt gratitude to the resource persons, Dr. R.Vembu, Dr. R.Roopkumar, and Dr. C.Ganesan for accepting our invitation to share their expertise with our young faculty. I must thank our beloved principal, Dr. Sister Jacinta Quadres, for her continuous encouragement and support to organize this webinar. I believe that this webinar will be profitable and fruitful for every one of you. Just a little housekeeping before we get started. If you have any questions during the presentation, please type in chat box in your control panel. We will bring them up after the presentation, and we will also have time for questions at the time. Thank you, one and all.
Ma'am, thank you for giving an outline on the various facets of the webinar. Now it's time to start the first technical session of the day. The resource person for this session is Dr. R.Vembu, sir, Associate Professor, Retired, Department of Mathematics, SBK Degree College, Aruppukottai, Tamil Nadu. Now, I invite Ms. PBL Sirisha Devi from the Department of Mathematics to introduce our honorable resource persons to the participants. Over to Sirisha, please.
A very good morning to you all and welcome to today's session. It gives me immense pleasure to introduce the resource person of this technical session. We are honored this morning by the presence of our honorable resource person, Shri Dr.R.Vembu, Associate Professor, Retired, Department of Mathematics, SBK College, Aruppukottai. Sir completed his PhD, MPhil and MSc from School of Mathematics, MK University, Madurai. He has 34 years of versatile experience in teaching from 1984 to 2017. Sir has published 14 papers in reputed international journals and presented his papers in various international and national conferences. Under his guidance, 35 students have been awarded MPhil and 2 students were awarded PhDs. He has written 3 books for Tamil Nadu Open University and also acted as a resource person, author, observer, and as a board member. Our distinguished resource person applied his extensive knowledge on presenting a software at the International Congress of Mathematics held at Hyderabad in the year 2010 and also completed a UGC minor research project on software to handle graph theoretical problems. Finally, on behalf of our college and department, I would like to thank you for accepting our invitation, sir. It's a great honor to have you in this national webinar. We would love to hear from you. Sir, I now request you to deliver the lecture. Thank you, sir.
Thank you very much, sir. Respected principal, management, and the head of the Department of Mathematics, and Ms. Sudha, respected participants, dear students, good morning to all of you. Thank you. First of all, let me thank all of you for giving me this opportunity. I think, is it audible? And what about the video?
Audible, sir. You're audible, sir.
Okay,
Video is also clear, sir.
Thank you. Now you will see only my slides, and if at all you have some doubt, I won't say see the chat box. If at all you have very important doubt, you call through your mic. Otherwise, you please mute your mics. Let me directly go into the title. Sequences and series. Many of the students should know what is a sequence and what is a series in undergraduate level also. Now, I think a few of you are teaching faculties and few of you are postgraduate MSc students. And so, the subject is not a new one. My talk may be a good recall for you, and the approach in my talk may be somewhat different. I hope you will enjoy this one. Let us start our talk from start our talk from a problem of cake, a sweet cake. Let us assume that there are 2 plates A and B, and a cake is placed on plate A, and we leave the plate B as empty. Then cut the cake in A into 2 equal parts, exactly 2 equal parts, and place one part in the plate B and leave the other in A. Again, cut the remaining cake in A into two equal parts, place the one part in B and leave the other in A. You go on doing this. What will happen finally? Avoiding the terms molecule, atoms and other things, what do you feel? What will be the amount of cake finally in A and finally in B? Let us see this stage by stage. At the beginning, in plate A, one full cake is available in plate A, and in plate B, 0 cakes are available. Again, after cut, the first stage is over, first cutting is over, the plate A contains half of the 1/2 part of cake and plate B contains 1/2. And after completing the second stage, plate A will contain 1/4 and plate B will contain 1/2 plus 1/2 is already there and 1/4 cake is the new piece. So, there will be 1/2 plus 1/4 cakes. After the third stage, 1/8 will be remaining and 1/2 plus 1/4 plus 1/8 will be in plate B and so on. If we go like this, at the nth stage, we will get to 1/2 power n part of cake in plate A and 1/2 plus 1/2 square plus etc. plus 1/2 power n cake in plate B. So, intuitively we feel that finally nothing will remain in plate A and a full cake will be available in plate B. In other words, the cake available in A is mathematically 0 and the cake available in B is 1. What do we get from this? What is the mathematics here? Intuitively, we feel that 1, 1/2, 1/4, 1/8, 1/16, etc. This goes to 0 and 1/2 plus 1/4 plus 1/8 plus etc. is equal to 1. Technically speaking, this is limit n tends to infinity, 1/2 power n equal to 1 to infinity. This is a sequence and this is a series. Give this. But mathematics will not accept this as a definition. An array of numbers, if I define a sequence as an array of numbers, then I have to say what is meant by an array. Unless I define array, that the definition is not a definition. Yes, a sequence is an array of numbers, it's not a definition. So we have to give a rigorous definition. As mentioned in your brochure, we have to give a very good rigorous definition. So these are some examples of sequences which by a sequence, now the meaning of sequence is what we have in our intuition. I have not defined what is meant by a sequence. Now, these are all examples of sequences. I want to give a rigorous definition. So what I do is, I write 1, 2, 3, etc. The first sequence we have, all of us learned in our first standard class. So I write 1, 2, 3, etc. this, and I associate this 1 to the first element of the sequence. I associate 2 to 1/3, 3 to 1/, etc. So this association motivate us to define a sequence as a function from the set of natural numbers to some set x. So a function from the set of natural numbers to any set x is called a sequence on x. Sometimes we consider finite sequences. The definition for a finite sequence is any function a from 1, 2, 3, etc. n to x is called a finite sequence on x. Usually we write functions like this, name of the function, the argument of the function like this. So hereafter, for sequences purpose, we denote them by a suffix n. So this is a definition for, this is the definition we give for a sequence and series. Sequences like this, we are not going to consider. Sequences A, B, C, etc. We won't consider sequences like this. We are going to consider only numeric sequence throughout this term. The numbers, the values of the function are real numbers or complex numbers. Let us have some pictorial representation of a sequence. For that, I take the two-dimensional XY plane. I mark 1, 2, 3, 4, etc. in the x-axis. If A of 1, A1, A suffix 1 is something, I mark that here. As this is 1 and this is A of 1. A of 1, A of 2, A of 3, A of 4, A of 5, etc. If I mark like this may be taken as a representation of a sequence in a picture. Suppose I am able to, so let this be a sequence. Suppose I am able to draw a line like this above all the elements, all the markings, then I can say that the sequence is bounded above. And similarly, if I am able to draw a line like this, I can say the sequence is bounded below. These are not rigor definitions. We shall give the rigor definition in a minute or two. Similarly, if I am able to draw two lines such that after some stage, all the elements are between the two lines, then we can say the sequence is convergent, and so on. So this is one way of representing sequence in a two-dimensional plane. When we plot the sequence like this, suppose the sequence is A1, A2, A3, if it is going up, never come down, then we can say the sequence is monotonically increasing, and similarly if it goes below, it's said to be a monotonically decreasing sequence. So anyhow, this is one way of representing this. But when we are talking about convergence of a sequence, a one-dimensional representation is better than these two-dimensional representations. They take the real line, and suppose I have a sequence. A1 is this point, A2 is this, A3, A4, etc., A5, etc. If we can mark the point on the real line, now we can talk about the bounded above, bounded below, etc., etc. Like this. Suppose I am able to mark a point so that all the points marked for the sequence are to the left of that point. Then that point may be called an upper bound. The sequence may be said as bounded above. And similarly, if I am able to mark a point here so that all the terms are to the right of that point, then that point is called, sequence is called bounded below. Is said to be a bounded below sequence. If it is both bounded above and bounded below, then we can talk about bounded sequences. And sometimes we may need some neighborhood under which all the points after some stage belong to that. That can be represented like this. These are all pictorial representations. This gives motivations for us to learn what is meant by a sequence. But a mathematician should give a rigor definition. We have so far discussed bounded above, bounded below, increasing, decreasing, monotonic sequence, convergent. A sequence is divergent, oscillating. These are all terms we have to define. Let me quickly recall and give the rigor definition for these terms. A sequence is said to be bounded above. All the sequences are AN. The first term is A1, second term is A2, third term is A3, etc. A sequence AN is said to be bounded above if I am able to find a capital M such that AN is less than or equal to M for all N. It is said to be bounded below if all the terms are greater than or equal to M after some stage. So for all N. A sequence which is both bounded above and bounded below is called a bounded sequence. Now, in other words, we can find two numbers N and M so that M is less than or equal to AN is less than or equal to M for all N. Similarly, increasing sequence, what do you mean by increasing sequence? A1 is less than or equal to A2, that is A2 is larger, A3 is larger than A2, A4 is larger than A3, etc. So, in other words, AN is less than or equal to AN plus 1 for every N. If so, then the sequence is called an increasing sequence. If it is the other way, AN greater than or equal to AN plus 1, then we say it is a decreasing sequence. If it is either increasing or decreasing, it is called a monotonic sequence. Here, it is bounded above and bounded below, then we say the function is bounded, the sequence is bounded, whereas for monotonicity, it is either increasing or decreasing. And when you study a book on sequences and series, some terminology here may change. Some people say increasing means an strictly less than an plus 1, and if an less than or equal to an plus 1, then they say non-decreasing sequence, and similarly non-increasing sequence or decreasing sequence. Some people may use strictly increasing and strictly decreasing. Anyhow, all the terms are self-explanatory. These are the definitions for. Let us see convergence. Convergence is the most important part of sequences in series study. A sequence A is said to converge to A. This is the definition. If given epsilon, there is a M naught such that something is true. But what this means? When you write this, all of you please say like this: a sequence A is said to converge to A if given any epsilon. In the old books, there will be something in the bracket, however small it may be. Even any small epsilon, if given epsilon greater than 0 is missing. If given epsilon greater than 0, there is a n naught, there is a stage n naught such that modulus of an minus a is less than epsilon for all n greater than or equal to naught. That is, after some stage, all the terms, this is distance from an and a, distance between an and a. Modulus of an minus a is the distance between an and a. So, after some certain stage, the distance between an and a is less than epsilon for the given small epsilon. If you give a very, very, very small epsilon, then also there is a stage, the stage may be somewhat larger, but there is a stage such that the distance between an and a is less than that epsilon also. If this is true for all epsilon greater than 0, then we say the sequence is convergent sequence. And a Gaussian sequence is another type of sequence. A sequence an is said to be a Gaussian sequence if given epsilon there is a stage n such that modulus of an minus am is less than epsilon for every n m greater than or equal to n naught. That is, after some stage, all the terms are very close to each other. That is what we mean by an minus modulus of an minus am is less than epsilon. We are not going to deal Gaussian sequences much because every convergent sequence is a Gaussian sequence. That can be easily proved. If an is a convergent sequence, say converging to a, then modulus of an minus am can be written as modulus of an minus a plus modulus of a minus am. So an minus a in modulus is less than some epsilon by 2. If I find a stage n such that n naught such that modulus of an minus a is less than epsilon by 2, then modulus of an minus a is also less than epsilon by 2 for every n greater than or equal to the stage. Therefore, modulus of an minus am is less than or equal to mod an minus a plus mod am minus am less than epsilon by 2 plus epsilon by 2 is equal to epsilon. Therefore, every convergent sequence is a Gaussian sequence, but the converse is not true. Converse is not true means in the set of rational numbers. In the set of rational numbers, let me construct a sequence. The first term is 1, second term is 1 plus 1 by 1 factorial. The third term is 1 plus 1 by 1 factorial plus 1 by 2 factorial. The fourth term is etc. So you know the sequence. This sequence converges to the limit is, the limit is E, but that E is not in Q. So the Gaussian sequence, this is a Gaussian sequence because all the terms are rational numbers. 1 by 1, 1 is a rational number, 1 plus 1, 2 is a rational number, 2 plus 1 by 2, 2.5 is a rational number, 2.5 plus 1 by 3 factorial 1 by 6 is also a rational number. So all the terms of the sequence are rational numbers. So we can call this as a sequence over Q, a sequence on Q, but this sequence doesn't find a limit in Q. Therefore, we say the sequence is not a convergent sequence in Q. But though the converse is not true in R, in general in R power n, every Gaussian in complex C power n, every Gaussian sequence is convergent. This is called a Gaussian criterion. So since we are going to consider real numbers or complex numbers for our discussion, for us, every Gaussian sequence is also convergent. So we are not going to deal Gaussian sequence separately. Okay. Now, what do you mean by a divergent sequence? A sequence is said to, AN is said to be divergent or diverges to infinity if all the terms are given any m. There is a stage such that all terms crosses that m. All terms are greater than or equal to that m. You give larger and larger m. In the old books, for any large m, for any given large m, they will write like this. But what do you mean by large m, small m? This, to avoid these disputes, I write for any given m. M is a real number. If m is given, then there exists a n naught such that there is a stage n naught such that after that stage, that is n greater than or equal to n naught, then an is greater than or equal to m. If so, we say the sequence diverges to infinity. Similarly, given any real number, suppose after some stage all numbers are less than or equal to that m, then we say the sequence diverges to minus infinity. If it diverges to infinity or diverges to minus infinity, we may say the sequence is a divergent sequence. When we consider complex numbers, there is only one infinity. So in that case, and there is no greater than or equal to and less than or equal to in complex field. Therefore, the definition for divergence of a complex sequence is a complex sequence is said to diverge to infinity if for any given m there exists n naught such that modulus of an is greater than or equal to m for all n greater than or equal to n naught. Oscillating sequence, finitely oscillating, infinitely oscillating are terms used by some people. Oscillating means it is neither convergent nor divergent. For example, you consider this sequence 1, 2, 1, 2, 1, 2, etc. This is neither convergent sequence nor it is a divergent sequence. This oscillates between 1 and 2. So it may be named as finitely oscillating sequence. Similarly, infinitely oscillating sequence. We can say, for example, 1, minus 2, 3, minus 4, 5, minus 6, 7, minus 8, etc. This sequence is neither convergent nor it is divergent. This is an unbounded sequence. Therefore, this is called infinitely oscillating sequence. Anyway, Rudin calls all such sequences by a single word divergent sequence. For Rudin, if a sequence doesn't converge, then it is called a divergent sequence. Right. How to prove a sequence converges to some limit? For example, let me consider the sequence 1 by n. This is the notation we use for sequence. Some people use double bracket and any term, any notation you can use. So I use this. The sequence 1 by n converges to 0. How to prove this one? We start anyhow, we are going to prove for a given epsilon, we want to find a stage after which modulus of an minus a is less than epsilon. So I start with an minus a. This an minus a is 1 by n and a is 0. So this is equal to 1 by n. Modulus of an minus a is less than 1 by n. So I want to find a stage after which 1 by n is less than epsilon. So 1 by n is less than epsilon if and only if n is greater than 1 by epsilon. So we take n naught in z such that a positive integer such that sorry. N naught such that this n naught is greater than 1 by epsilon. If n is greater than or equal to this n naught, then that n is greater than 1 by epsilon, and therefore 1 by n is less than epsilon. Therefore, mod an minus a is less than epsilon. So, in this way, we can find a stage for which the mod an minus a is less than epsilon. Let me consider another example. 1 by n square plus 3. This sequence also, if I consider mod an minus a, then it is equal to 1 by n square plus 3. So 1 by n square plus 3 is less than epsilon if and only if n is greater than or equal to this one, greater than this one. So if we take n naught in z so that n naught is greater than this value, then for any n greater than or equal to n naught, modulus of a n minus a will be less than epsilon. Therefore, this sequence converges to 0. But this is not a good way to find the convergence of a sequence. Many times we are interested in finding whether a sequence is convergent or not. So see, for example, you cannot find a stage. It is not easy to find a stage for which this sequence is less than epsilon. A n is modulus of a n minus a is less than epsilon. Unless you know the limit, you have to. We cannot work like this. So what mathematicians do is we develop properties. Suppose I have a property that a sequence is of this form. The numerator is a sequence, denominator is a sequence. If numerator converges to a and denominator converges to b, then the entire sequence may converge to a by b under certain conditions. So we can separate these sequences, and for the denominator sequence there are two sequences. One is n square, another one is sine of something. So if I know this sequence converges to some limit, this sequence converges to some limit or diverges to infinity, something like that, then we can say something about the entire sequence. So we develop properties. These properties are easily developed. For example, if a n and b n are two sequences converging to a and b, then the new sequence a n plus b n converges to a plus b. This is a very simple result. Let me just recall the proof. Suppose some epsilon is given. I want to find this. Let me call this as Cn and this as C. I consider modulus of Cn minus C. Modulus of Cn minus C is nothing but modulus of An plus Bn minus A plus B. That is nothing but, that is equal to modulus of An minus A plus Bn minus B. That is less than or equal to mod An minus A plus mod Bn minus B. This mod An minus A may be made less than epsilon after some stage because An converges to A, and mod Bn minus B similarly can be made less than epsilon by 2. And therefore, mod Cn minus C is less than epsilon by 2 plus epsilon by 2 is less than epsilon. And therefore, the series such a sequence an plus bn converges to a plus b. And similarly, if an minus an, the new sequence an minus bn converges to a minus b, some constant times if I multiply a sequence can, because I am multiplying each term by say 2, then the limit is 2 times the previous limit, and the product converges to the, if an by bn is the nth term of a new sequence, an converges to a and bn converges to b, then an by bn converges to a by b. But there are some conditions here. This b and bn, there is something in the denominator should not be 0, because if denominator is 0, we have no meaning in writing an by bn or a by b, and therefore when bn and b are not equal to 0, then an by bn converges to a by b. And if an and bn are two sequences converging to a and b, and an less than or equal to bn for all n, or after some stage, if an less than or equal to bn for all n after some stage, then the limit is also a less than, we have a less than or equal to b. In case of divergence also, we can talk something like this. Suppose an diverges to infinity and bn diverges to infinity, then an plus bn diverges to infinity. But in the case of if an diverges to infinity and bn diverges to minus infinity, we cannot say an minus bn may converge, it may diverge to infinity, or it may diverge to minus infinity, and so on. Anyhow, we are interested only in convergence sequences. Some results like this. If an is bounded and mod bn converges to infinity, then an by bn tends to 0. So for this, this bn is this an is bounded. Sign of something, whatever be the something, this lies between minus 1 and 1. Therefore, the numerator is bounded. The denominator is n square plus some number. That some number lies between minus 1 and 1. So this becomes larger and larger and tends to infinity. Therefore, this is bounded, this tends to infinity. Therefore, the limit is 0. So this result helps us. And if a sequence bn lies between two sequences an and bn, and if this an and cn converge to same limit a, then that bn must also converge to the same limit a. These are all some properties of this. Okay. Now let us find limit of sequence. In undergraduate, even in high school classes, you have this type of sequences. What is the limit? Let me explain the process of finding limit and then. So I take an n out. So this becomes 2 n into 2 by 3 by n, 2 plus 3 by n, and the denominator is n into 3 by 2 plus n. So now I can cancel this n and get this 2n plus 3 by 3n plus 2 is nothing but 2 plus 3 by n by 3 plus 2 by n. Now if I take limit, for the numerator also, separately let me take limit of the numerator. As n tends to infinity, this 3 by n becomes 0, and therefore 2 plus 3 by n tends to 2, and this 3 plus 2 by n tends to 3, and therefore the given sequence tends to 2 by 3. This is this we have did in our school life also. Similarly, for this we can take n out and so on. 2n square plus 3 by n square, n by 2 tends to infinity. From this, these examples are like this: a polynomial divided by another polynomial. If given a polynomial a sequence like this, a polynomial divided by another polynomial, then without doing all these computations, we can directly write if the degree of the numerator is less than degree of the denominator. That is something like here. Degree of the numerator is less than degree of the denominator, then the limit is 0. If the degree of the numerator is larger than degree of the denominator, something like this, then the limit is infinity or minus infinity. Something, suppose here is minus is there, it may diverge to minus infinity. And if degree of n is equal to degree of the denominator, degree of numerator is equal to degree of the denominator, then the limit is the coefficient of the leading coefficient of the numerator divided by the leading coefficient of the denominator. Okay. Let us see some special sequences. See, 1 by n tends to 0. This we know. 1 by n square tends to 0. 1 by root n, 1 by cube root of n, etc. All these things tends to 0. In general, 1 by n power p tends to 0 if p is greater than 0. The proof is a single line proof. To prove this one, what we consider? We consider mod an minus a. Mod an is modulus of n power 1 by n power p. A is 0. So since all the terms are positive, mod an minus a is nothing but 1 by n power p. I want this 1 by n power p to be less than epsilon. This is true if and only if n power p is greater than 1 by epsilon. So in other words, n is greater than or equal to greater than 1 by epsilon power the pth root of 1 by epsilon power 1 by p. So if n naught is taken as an integer greater than 1 by epsilon power 1 by p, then we see that 1 by n power p is less than epsilon for all n greater than or equal to that n naught. So we see that 1 by n power p tends to 0. And similarly, what is the nth root of a fixed number? For example, if you have a calculator in your hand, you can apply 2 and then find the square root. For that, find the square root, that is 4th root of 2, and then find the square root of that, 8th root of. You will get 1 after some stage because the calculator is deals with only finite numbers. Infinite, it cannot go to infinite time. Anyhow, 2 root 2, cube root of 2, 4th root of 2, etc. that converges to 1. So in general, if p is greater than 0, even if you take 1 by 2 and find the square root of 1 by 2, cube root of 1 by 2, 4th root of 1 by 2, and so on, you will get the term will approach to 1. If p is greater than 1, greater than 0, nth root of p tends to 1. Let us see a proof. Proof is also simple. first I start with p greater than 1. You write down xn as nth root of p minus 1. Nth root p, since p is greater than 1, nth root of p is greater than 1. Therefore, nth root of p minus 1, that is xn, is greater than 0. From this, we can say nth root of p is equal to xn plus 1 or p equal to 1 plus xn power n. We can expand this using binomial theorem, that is 1 plus nxn plus nc1 1 power 1 power 2 xn square and so on, finally xn. And this is greater than, these are all positive terms, so I leave all these terms. Therefore, this is greater than 1 plus nxn. You see, p is greater than 1 plus nxn, so nxn is less than p minus 1, that is p minus 1 by n is greater than xn. This xn is greater than 0. This tends to 0. P minus 1 by n. P minus 1 is a fixed number, it's a bounded number, by n. As n increases, this p minus 1 by n tends to 0. This also tends to 0. Therefore, the sequence between these two sequences also tends to 0. So, xn tends to 0. Xn tends to 0 means nth root of p minus 1 tends to 0. So, nth root of p tends to 1. If p is greater than 1. When p equal to 1, the result is very obvious. That is, this is 1, 1, 1, 1, 1, etc. That equals to 1. If p is less than 1, we just take the reciprocal and we get the result. Okay. Another sequence is nth root of n. Nth root of n also tends to 1. Similar proof, xn, to write xn right as nth root of n minus 1. Nth root of n is always greater than or equal to greater than 1. Therefore, this minus 1 is greater than 0. I write n as like this. So, xn plus 1 is nth root of n. But power raising to the power n, we get n equal to 1 plus xn power n. I expand this by using binomial theorem. I have only this term with me and leave all other terms. All other terms are positive terms. Therefore, this is greater than n into n minus 1 by 2 xn square. Using this, we see that after cancelling n is greater than n minus 1 by 2 into xn square. So, square root of 2 by n minus 1 is greater than xn. That is greater than 0. This goes to 0, this goes to 0, and therefore the sequence n power n goes to 1. Similarly, the sequence x power n. X power n also tends to 0 if 0 less than x less than 1. A similar proof. If x is 0, what will happen? If x is 0, then the sequence is nothing but 0, 0, 0, 0. That goes, so the limit is 0. If x lies between minus 1 and 0, then considering minus x in the place of x, we see that also tends to 0. If x is greater than 1, if x equal to 1, the sequence is 1, 1, 1, 1, etc. That converges to 1. If x is greater than 1, the series diverges to infinity, and x less than minus 1, then it oscillates like this. For even squares, even powers is positive. For odd powers, it is negative. But the absolute value becomes larger and larger. So it infinitely oscillates. In Rudin's language, it is a divergent sequence. Another important concept in the study of sequences is subsequences. Let us consider the sequence 1, 1 by 2, 1 by 3, 1 by 4, etc. I consider this sequence. I erase certain terms of the sequence. Say I left first term, third term, fifth term, and so on. For uniformity, I do like this. You can erase any terms, any number of terms, but you have to leave infinitely many terms. After erasing these terms, if I write this as a sequence that is without any space, then this sequence is maybe called as a subsequence of the given sequence. In particular, this is A2, A4, A6, A8. Suppose this is A1, A2, A3, A4, A5. Then this is A2, A4, A6, etc. So this A2, A4, A6, etc. is a subsequence of A1, A2, A3, etc. If you look at the suffix is increasing. You should not change the order. When writing subsequences, you should not change the order. We have to keep the order. We may leave some terms. So this suffix must be less than or equal to this suffix. This must be the suffix must be less than or equal to the. Don't confuse with suffix and terms. Suffix must be less than or equal to this suffix and so on. So N1, if I choose N1, N2, N3, N4, etc. for the suffix as the suffix of the new sequence, then this N1 must be less than N2 and this N2 must be less than N3, etc. So this is a strictly increasing sequence of natural numbers. So if AN is a sequence and N1, N2, N3 is an increasing sequence of positive integers, that is strictly increasing sequence of positive integers, then the sequence ANK is called a subsequence of A. And this is the rigor definition for a subsequence. What is the use of subsequences? Before that, let us fix a notation. This is used by Ruding. Therefore, if a sequence AN converges to L, then we write, already we have written AN tends to L. If a sequence diverges to infinity R to minus infinity, then we write AN tends to infinity R tends to minus infinity. So, we use the sequence tending to L, where L is a finite real number, R infinity, R minus infinity. If AN is a sequence and there is a subsequence of AN tending to L, then that L is called a subsequential limit of AN. So, subsequential limit is nothing but limit of a subsequence. Okay. We can see some results. If AN converges to A, then every subsequence of AN converges to A. And if AN diverges to infinity, then every subsequence of AN will diverge to infinity. And if AN diverges to minus infinity, then every subsequence of AN diverges to minus infinity. And the converse of these things also true. If every subsequence of AN converges to A, then AN is a convergent sequence converging to A, and if every subsequence of AN diverges to infinity, then AN itself diverges to infinity and so on. So every sequence has at least one subsequence limit. So we can talk about the infimum of or supremum of that subsequence limits. Let us construct some subsequences having only one subsequence limit. Can you give an example of a sequence having only one subsequence limit? That means all subsequences either have limit or they do not. There is only one limit or they do not converge. In other words, but we know a sequence has exactly one limit. Means it is a convergent sequence. All subsequences of a convergent sequence are convergent sequence. So, see, for example, you consider this sequence 1, 1, 1, 1, 1, 4. You take whatever be the subsequence that can also the sequence 1, 1, 1, 1, 1 that converges to 1. So, 1 is the only subsequence limit. You can take any convergent sequence. The limit of the convergent sequence is the only subsequence limit of that sequence. Can you give me a sequence having exactly two subsequence limits? See, for example, take two sequences, one converging to A and another converging to B. The A1, A2, A3, A4, etc. are converging to A and B1, B2, B3 converging to B. I write this A1, A2, A3 like this and B1, B2, B3 like this. I merge these two sequences. by writing A1, B1, A2, B2, A3, B3, etc. This sequence, we can prove that this is a sequence, of course. This sequence has this subsequence A1, A2, A3, A4, etc. That subsequence converges to A and has a subsequence B1, B2, B3, B4, etc. That converges to B, and we can prove that there is no other sequence if this A and B are not equal to 0. If A is not equal to B, then there is no subsequence for this sequence converging to both, converging to some other limit. So every convergent subsequence must converge to either A or B. So the set of subsequence limits is a two-term set, a set containing two elements. One is A and another is B. Now can you construct a sequence having exactly three subsequence limits? The same technique. You take three sequences, A1, A2, A3 converging to A, B1, B2, B3 converging to B, C1, C2, C3 converging to C, and this A, B, C are pairwise distinct. Form the sequence A1, B1, C1, A2, B2, C2, A3, B3, C3, and so on. That new sequence will have exactly three subsequent limits. Can you give a sequence having countably many subsequence limits? Is it possible? This technique, what we discussed for 2 or 3, will not work here. But we can construct a sequence having countably many subsequent limits. Say, for example, let me take all the integers 1, 2, 3, positive integers 1, 2, 3, 4, etc. Let the first sequence converge to take a sequence converging to 1, take a sequence converging to 2, take a sequence converging to 3, and so on. So A11, A12, A13, etc. This sequence converges to A1, A21, A22, A23, etc. converges to A2. Similarly, like that. So if we consider this sequence, now I am going to write a new sequence. The first term of the sequence is A11. The second term is A21 and then A12. Third term. Fourth term is A31, A22, A13, A41, A32, A23, A44, and so on. So diagonally we exhaust all the elements. So this sequence, we can prove that A1, A2, A3, A4, etc. are subsequence limits. Suppose this A1, A2, A3, etc. has a limit point. Limit point will be dealt in metric spaces. That also will become a subsequence limit. So if we choose A1, A2, A3 like 1, 2, 3, 4, etc., then the subsequence limits is countably many subsequence limits. Uncountably, can we have a sequence having uncountably many subsequence limits? All real numbers are subsequence limits. We can have a sequence having all real numbers as subsequence limits. The sequence is very simple sequence. We know Q is countable. Write down all the elements of that countable set in a sequence. That sequence has all real numbers as subsequent limits. So another question is, given any set of real numbers, can we form a sequence whose subsequence limits, the set of subsequent limits is same as the given set? This is not always possible because, for example, if we take 1, 1 by 2, 1 by 3, 1 by 4 as the given set, we can form a sequence which has subsequence limits as 1, 1 by 2, 1 by 3, etc. For that sequence, 0 will also be a subsequence limit. So we cannot, the subsequence limits is, we cannot find a sequence whose subsequence limit is exactly this one. So is there any condition? Yes, there is a condition. The set must be closed. In that case, take a countable dense subset and proceed. We get a subsequence sequence having the given set as a subsequent set of subsequence. Okay. At this moment, the infimum of the set of subsequence limit is called limit infimum, and the supremum of the subsequent set of subsequent limit is called limit supremum. But what do we mean by that? They are called upper and lower limits. Let me give a different approach for upper and lower limits. Let AN be a convergence sequence. Let us start with a convergence sequence. If AN is a convergence sequence, some epsilon is given. Then, if I consider if I consider A minus epsilon, there may be at most finitely many terms less than that A minus epsilon. Because after some stage, all the terms of the convergence sequence lies between A minus epsilon and A plus epsilon. So there are only finitely many terms to the left of A minus epsilon. That is, there are only finitely many terms less than A minus epsilon. There may be zero terms. There may not be any term. However, we cannot have infinitely many terms outside A minus less than A minus epsilon if the sequence converges to A. And similarly, if the sequence converges to A, we cannot find infinitely many terms greater than A minus epsilon. All the terms will be between A minus epsilon and A plus epsilon. This we know. That is, for any epsilon greater than 0, there are only finitely many terms of the sequence outside A minus epsilon. The converse is also true. That is, we can find an A satisfying this property. That is, all the terms are between, for any epsilon, only finitely many terms are outside A minus epsilon and A plus epsilon. Then we say the sequence converges to A. This is our convergent sequence. When we take a non-convergent sequence, we cannot find such an A. So, if I am able to find two numbers, A and B, or let me concentrate only on A. If I am able to find an A such that for any epsilon greater than 0, there are only finitely many terms of the sequence less than A minus epsilon. In some sense, we can call this as infimum of AN. This is not the infimum of the set of all points in AN. But anyhow, only finitely many points are less than this. All other terms are greater than this. Therefore, we say, we can, in some sense, that's why I write some sense, this A is called, may be called as an infimum of this AN. If A is such a number, and if I take any number less than that, that is also an infimum. So, we are interested in finding the largest of such infimums. In other words, I find the supremum of these infimums, the limit of this increasing, if I, the upper limit of that infimums, if I take, that infimum may be called as limit infimum. And similarly, we can define limit supremum. That is, we can find B, say B, such that for any epsilon greater than 0, there are only finitely many terms of the sequence greater than A plus epsilon. In some sense, that can be called as a supremum of AN. And if A is a supremum, as a B is a supremum, and something is greater than that number, that is also a supremum. So, we are interested in finding the least of such supremums. That supremum is called, the limit of such supremum is called limit supremum. This is one approach to limit infimum and limit supremum. Limit supremum and limit infimum are called upper limit and lower limit. How to find this upper limit and lower limit? For that, the definition given in Rudin is very nice. See, for example, this is a sequence, minus 1 by 2, 1 plus 1 by 2, minus 1 by 3, 1 plus 1 by 3. I think you can follow the sequence. For this sequence, if I consider, what are the subsequence limits? Minus 1 by 2, minus 1 by 3, minus 1 by 4, minus 1 by 5, that goes to 0. And 1 plus 1 by 2, 1 plus 1 by 3, 1 plus 1 by 4, that goes to 1. And it has no other subsequence limits. If any epsilon is given, if I take A as 0, if I take A minus epsilon, say A minus 1 by 100, there may be only 100 terms less than A minus epsilon. Namely, minus 1 by 2, actually 99 terms, minus 1 by 2, minus 1 by 3, minus 1 by 4, minus 1 by 100. These terms are less than 0 minus 1 by 100. And other terms are greater than A minus epsilon, 0 minus epsilon. So, whatever be the epsilon given, this sequence has only finitely many terms to the left of that A minus epsilon. And similarly, above 1 plus epsilon, there are only finitely many terms. So all terms are many. So if I take the neighborhood a minus epsilon and b plus epsilon, and if I make the epsilon smaller and smaller, I can get two bounds. One is limit infimum, and the A is limit infimum, and the other one is limit supremum. So this may be taken as the definition. This is the definition given in Rodin. Let A n be a sequence of real numbers. Let E be the set of subsequence limits of A n. This may contain infinity minus infinity also. Then infimum of this set E is called limit infimum A n, and supremum of this set E is called limit supremum of. If A n is a convergence sequence, then we know that convergence sequence, for that convergence sequence, all subsequences will also converges with the same limit, and therefore E contains only one element, namely the limit. Therefore, the limit, infimum of E is, suppose A n converges to A. Infimum of E is A, supremum of E is also A. Therefore, limit infimum A n is equal to limit supremum A n, that is equal to limit of A. And conversely also, if limit infimum and limit supremum are equal, then that is equal to limit of the sequence. That sequence, the convergence sequence, and the limit is given by this equal number. And results like if A n less than or equal to B n, then limit infimum less than or equal to limit infimum of B n, limit supremum of A n less than or equal to limit supremum of B n. So these are all. I think now we can start a series. In the beginning, we started with a cake problem of cake, isn't it? We said the plate B contains the full cake, and technically we write like this: 1 by n, limit sigma n equal to 1 to infinity, 1 by 2 power n is equal to 1. That is 1 by 2 plus 1 by 2 square plus 1 by 2 cube, etc. What is plus? Plus is a binary operation. I have a question. Addition, that is plus, is a binary operation in which can be also we can operate only two elements at a time. That can be extended to finitely many numbers. If I have four numbers, I can add first number and second number. That becomes a single number. This single number plus the third number, that becomes a single number. And with that, I add the fourth number. When commutativity, associativity are true, then we can change the order and other things. Anyhow, we can extend the operation addition to only finite sets. Finitely, if I take finitely many numbers, I can add. But how to add infinitely many numbers? We won't finish that job of adding all numbers. You can add first number and second number. With that answer, you can add the third number, you can add the fourth number, you can add the numbers A1, A2, A3, A4, etc. But the problem, the work of adding the number will never end because there are infinitely many numbers. But we intuitively feel that this sum is 1. So we need a method and a rigor definition for that. In general, what do you mean by A1 plus A2 plus A3 plus A4, etc.? We have to give a meaning first. So I start with the sequence A1, A2, A3, A4, etc. I'm going to construct a new sequence. The new sequence is, the first term of the new sequence is A1, second term is A1 plus A2, third term is A1 plus A2 plus A3. So this is a sequence. We know a lot of things about sequences. If this sequence converges to some limit S, then we can say this sum is S. We say that the series, the sum of all these terms, A1 plus A2 plus A3 plus etc. is equal to S. This makes sense, isn't it? The first term is A1, second term is A1 plus A2, third term is A1 plus A2 plus A3. So if I do like this, what I get is finally is the limit of this sequence. So if the limit of the sequence exists, that is, if the sequence converges, this sequence is called a sequence of partial sums. Suppose this sequence converges to S, then I can define this as the sum of these things. So we have this definition. So A1 is a sequence, Sn is A1 plus A2 plus An. If the sequence Sn converges, then the sequence A1, A2, A3, A4 is said to be summable. This sequence is summable. I can add these things. It is summable sequence. And we write A1 plus A2 plus A3 plus S equal to S. The sequence Sn is called a sequence of partial sums. Okay? So, by our intuition, we see that this sequence is summable. We have not yet proved that this sequence is summable, but we will prove. This is summable. What about and 1 by 2 plus 1 by 2 square plus etc. is equal to 1. Summable, that sum is 1. Therefore, this we got from the Kate problem, and we, in our intuition, we have not proved this. Anyhow, what about this sequence? The term is 1, minus 1, 1, minus 1, 1, minus 1, etc. So, the partial sum sequence is, the A1 is 1, and A1 plus A2 is 1 minus 1, 0, and then A1 plus A2 plus A3 is 1, A1 plus A2 plus A3 plus A4 is 0, and so on. So the partial sum sequence is 1, 0, 1, 0, 1, 0, 1, 0, etc. It is not a convergent sequence. Therefore, this sequence is not summable. 1 minus 1, 1 minus 1, 1 minus 1 is not a summable sequence. So this has no meaning. 1 minus 1 plus 1 minus 1 plus 1 minus 1, etc. has no meaning. However, so A1 plus A2 plus etc. this has a meaning or not depends upon the convergence of the partial sum sequence. So before knowing the convergence of the partial sum sequence, we cannot write like this. But consider the partial sum sequence, we may write like this. The old practice, it's a very old practice to call this as a series. If this converges, then we say A1, A2, A3 is, this is a modern term, A1, A2, A3, etc. is summable. So, but whether it is summable or not, if we write like this, they call this as a formal sum. The sum has no meaning. This is a formal sum. This formal sum is called series in the olden days. So we shall also call this as a series without worrying about the convergence of partial sum. Okay. This we have discussed. A series sigma an is said to be when the index is not very important. We leave the writing the index here, running index. The series sigma an is said to be convergent if the partial sum sequence is convergent. We are interested only in convergent series. Okay. What about this series? Whether this converges? No, because the partial sum sequence is 1, 2, 3, 4, etc. This is not convergent. Why it is not convergent? We add infinitely many terms. But the total sum must be number means the amount of the number, the magnitude of the number must be very, very small when we add. You just recall your Archimedean property. If we add even a small number, epsilon, many times, then that will cross any given number. In other words, what is Archimedean property? Given any epsilon greater than 0 and any m, however large it may be, then we can find a n such that n into epsilon is greater than that m. So, even if you repeatedly add a small number, that sum will become infinity. Therefore, the quantity of the magnitude of the number we add must be smaller and smaller and smaller. So, in other words, if sigma an is convergent, then the sequence AN must converge to 0. Listen. Okay. This is easy to prove. Let us prove this. If Sn is convergent, since Sn is convergent, sigma, let us assume that sigma n is convergent. Sigma n is convergent means the partial sequence Sn is convergent. Sn is convergent means Sn is Cauchy. So, for any given epsilon greater than 0, there is a stage n0 such that modulus of Sm minus Sn is less than epsilon for all m n greater than or equal to n0. So, if I take m as n plus 1, then Sn plus 1 minus Sn is less than epsilon for all n greater than or equal to n0. Sn plus 1 minus Sn is nothing but an plus 1. So, an plus 1 is less than epsilon for all n. In other words, an plus 1 converges, that is an converges to 0. Okay. So, with the help of this theorem, this result, we can say, we can see some sequences like this, 1 plus 1 plus 1 plus 1 is not convergent, but it is only a necessary condition. From this, we cannot say 1 plus 1 by 2 plus 1 by 3, etc. or 1 minus 1 by 2 plus 1 by 3 minus 1 by 4, etc. Whether it is converge or not, we cannot say using this theorem. This is only a necessary condition. We will see later that this sequence is divergent, the sum is infinity, and this sequence is converged. A series of non-negative terms converges, some results, non-negative term converges, even only if its partial sum sequence is bounded. Because terms are non-negative means partial sum sequence is an increasing sequence. Therefore, if it is bounded, that any increasing sequence which is bounded above is convergent. Therefore, if a series of non-negative terms, the partial sum sequence is bounded, then the series is convergent. If sigma an converges, then sigma minus an also converges, and the limit is if the sum is yes, the sum of sigma minus an is minus s. Similarly, what we proved for sequences, if sigma an converges, sigma bn converges, sigma an plus bn converges, if 0 less than or equal to an less than, this is a comparison test. It's an interesting one. If 0 less than or equal to an less than or equal to bn, the terms of sigma an, and I compare the terms of sigma an and sigma bn. This, let me call this a smaller sequence, this is a bigger, larger sequence, larger series. Each term of sigma an is less than or equal to each the corresponding term in the series sigma bn, and I know sigma bn is convergent. Then automatically we can say sigma n is convergent. Anyway, we have to give a rigor proof, but we feel that the larger sequence itself, the sum is say 10. Then the smaller series, the sum of the smaller series is less than or equal to 10, because all the terms are, of course, I assume non-negative. If mod an is less than or equal to bn, sigma bn is convergent. The larger series is convergent, then sigma an is convergent. So, for example, if all an are positive, then that follows from this one. If all ans are negative, then the negative of that sequence is consists of only positive terms, and using this we can arrive and so on. Anyhow, these are all simple results. Proof is available in any book. When comparing this, if the smaller sequence is divergent, all terms are non-negative terms. So if the smaller sequence is divergent, then the larger sequence must diverge. These facts can be obtained from intuition also. Series like this are called geometric series, 1 by 2, some number plus the square of that some number, the cube of that number, 4th power of that number, and so on. That is x power n is called a geometric series. This many of you learned in school itself. What about the convergence of the geometric series? If Sn equal, what is Sn? Sn equal to 1 plus x plus x square plus etc. We have taken n plus 1 terms. Don't worry about these things. We can write that as Sn. If you are, that is, you change if needed. If you want to convince yourself, you can change the definition of Sn as 1 plus 2 plus up to n plus 1 times. Anyway, this Sn, if I calculate, I get this one. So what is the limit of Sn? Limit of Sn is limit of this as n tends infinity. 1 minus x, everything is constant. This x power n only vary as n varies. But when your x is, modulus of x is less than 1, then this tends to 0. That we have seen in the sequences part. So this tends to 0, therefore 1 by 1 minus x. So sigma x power n converges if mod x is less than 1 and the limit is 1 by 1 minus x. And if when x equal to 1, the series is 1 plus 1 plus 1 plus 1, etc. That diverges to infinity. And when x is minus 1, 1 minus 1 plus 1 minus 1 plus 1 minus 1, that has no meaning. It is not a convergent sequence. And for larger value of x, that is if n equal to x equal to 2 or something greater than 1, then obviously this each term itself becomes larger and larger, and therefore we cannot get that an tends to 0, xn tends to 0, and therefore the series cannot converge. So 1 plus 1 by 2 plus 1 by, if I take x equal to 1 by 2, then this is 1 by 1 plus etc. From this part, that is 1 by 2 plus 1 by 2 square plus etc. The entire total is 2. I leave this 1. So therefore 1 by 2 plus 1 by 2 square plus 1 by 2 cube plus etc. is equal to 2 minus 1 is equal to 1. So in other words, what we felt intuitively in the cake problem, that is 1 by 2 plus 1 by 2 square plus 1 by 2 cube etc. is equal to 1, match with the regular definition of convergence and so on. We need not know all about all terms. If we know the sequence, the terms of the series A1, A2, A3, etc. decreases to 0, then the convergence of An can be obtained from computing this value, that is A1 plus 2 times A2 plus 4 times A4, 8 times A8, etc. In general, 2 power n times A2 power n, 2 power nth term of the sequence multiplied by 2 power n. If we add all these numbers, suppose this series converges, then sigma an converges. If sigma an converges, then this series converges. So in other words, the convergence of sigma an is same as this one. Nothing is special in 2 and you can even take 3, 9, 27, etc. That also, then also we have sigma an converges if and only if this series converges. And we can talk about the convergence of sigma 1 by n power p. The proof is simple. Sigma 1 by n power p converges if and only if p is greater than 1. We can use the previous theorem. Here, the terms are becoming smaller and smaller. So sigma n power p, p is greater than 1. So n power p becomes larger and larger. So 1 by n power p becomes smaller and smaller, and that tends to 0 as n tends to infinity. N power p, since p is greater than 1, n power p tends to infinity. 1 by n power p tends to 0. So this satisfies the hypothesis of the previous result. If I calculate this one, sigma 2 power k a 2 power k, then that is equal to 2 power k, 1 by 2 power k power p, and so on. The convergence of this series depends upon this number. 2 power 1 minus p whole power k. So 2 power 1 minus p, suppose, is less than 1, if and only if 1 minus p is less than 0, if and only if 1 less than p. So the result follows for p greater than 0. If p is less than 0, we can take an as 1 by n power p, n power minus p. This doesn't tend to 0. So the series is not a convergent series. So this follows. Similarly, we can prove the convergence of 1 by n factorial. 1 by n factorial, this series, this is nothing but E. isn't it? The proof is simple. Sn equal to 1 plus, we use the comparison test, 1 plus 1, I expand in this way. 1 plus 1 by 2, Sn is 1 plus 1 plus 1 by 1 into 2, 1 plus 1 by 1 into 2 into 3, etc. 1 by n factorial. I write 1 here, I write 1 here. Instead of, this is 1 by 2, instead of writing 3 here, I just put 2. In other words, I am decreasing the denominator. Decreasing the denominator means the value of the number becomes larger. So 1 by 2 square is larger than 1 by 3 factorial. Similarly, 1 by 2 cube. In 1 by 2 cube, we have 1 by 1 into 2 into 3 into 4. I leave 3. So there are 3 2's. So I am decreasing the denominator, and therefore the entire value becomes larger. So each term of this is greater than or equal to each term, the corresponding term of the term in the Sn, and therefore this part is less than this. But what is this? This is less than, we have seen that 1 by 2 plus 1 by 2 square plus 1 by 2 cube plus 1 by 2 for n minus 1 plus something is equal to 1. So this is less than 1. Therefore, the entire thing is less than 3. Therefore, Sn is less than 3. In other words, the partial sum sequence Sn is bounded above by 3. Clearly, since the terms are non-negative, Sn is an increasing sequence bounded above, and therefore Sn is convergent. That converges to some number. That number is the famous E. This E is a very useful number in the theory of mathematics, and therefore that can be obtained as a sequence also. This is a famous theorem. Limit n tends infinity 1 by 1 plus 1 by n whole power n is equal to E. We can enjoy the technique used in this theorem. So we can prove this in 2 slides. Let us start. The nth partial sum of the series I denote by Sn, and the nth term of the series sequence as Tn. Now what is Tn? Tn is equal to 1 plus 1 by n whole power n. That I can expand using binomial theorem. That is 1 plus n into 1 by n plus nc 2 into 1 power n minus 2 into 1 by n square, and so on. nc 3 into 1 power n minus 3 into 1 by n power 3, etc. Therefore, Tn is this one. That is equal to 1 plus this n and this n will get cancelled. So 1 plus, I take an n out here. So n, this term n minus 1 is n into 1 minus 1 by n. So there are 2 n's in the numerator, n square. There is an n square in the denominator, they get cancelled. And here I can take an n from here, an n from here, and therefore the numerator becomes n cube into 1 minus 1 by n into 1 minus 2 by n. There is an n cube here, that n cube will get cancelled. So we get 1 by 3 factorial into 1 minus 1 by n into 1 minus 2 by n, and so on. In the nth term also we get. So Tn is less than this. What is this? This is nothing but Sn. No, sorry. Now take the limit. When you take limit as n tends to infinity, we cannot take limit now. We can Sn is this part is less than Sn. What is Sn? Sn is 1 by 2 factorial. This is less than 1. This is less than 1. This is less than 1. Therefore, the product is less than 1. The product is less than 1. So the entire total is less than or equal to 1 plus 1 plus 1 by 2 factorial plus 1 by 2 3 factorial plus 1 by 4 factorial, etc. 1 by n factorial. Therefore, that is Sn. So this Tn is less than Sn. Now, if we take limit supremum on both sides, then limit supremum of Tn, that we don't know what is limit supremum of Tn, but limit supremum of Sn we know, because Sn is a convergent series. We have proved just now, the previous slide. So, limit supremum of Sn is limit of Sn. That limit of Sn is E. Therefore, limit supremum of Tn is less than or equal to E. On the other hand, I fix, suppose you take some n greater than m, and what is Tn? This Tn is greater than or equal to Tn is equal to 1 plus 1 plus this. Some more terms will be there up to n, but I cut a few terms. After the mth term, I cut everything. Therefore, Tn is larger than this one. Now, I keep m fixed and take limit as n tends to infinity, or limit infimum. So, limit infimum of Tn is greater than or equal to limit infimum of this. Limit infimum of this is limit of this as n tends to infinity. I keep m fixed. So, this is 1, this is 1, and this is 1 by 2 factorial. This becomes 0, and therefore I think some noise is there. N tends to infinity, this becomes 0, this becomes 0, therefore this is 1, this is 1, this is 1, therefore 1 by 3 factorial, etc. And therefore, limit infimum of Tn is greater than or equal to 1 plus 1 plus, etc., 1 by 2 factorial plus 1 by 3 factorial, etc., 1 by m factorial. Now, this is true for every m. Now, take limit as n tends to infinity. This is a single number, this will be there, and this becomes E. Therefore, limit infimum Tn is greater than or equal to E. I write this in another way, that is E is less than or equal to limit infimum of Tn. For any sequence Tn, limit infimum is less than or equal to limit Tn, because limit supremum Tn. Limit infimum is less than or equal to limit supremum Tn, because limit infimum is after all infimum of a set, and supremum is limit supremum is supremum of the set of subsequential limits. Therefore, infimum is less than or equal to supremum. Therefore, limit infimum of Tn is less than or equal to limit supremum of Tn. But limit, we have proved in the previous slide that limit supremum of Tn is equal to E, less than or equal to E, and therefore all these things are equal. In other words, limit infimum Tn is equal to limit supremum Tn is equal to E. As if these two are equal, we see that the limit exists and the limit is E. That is what we want to prove. And there are some tests available to find whether a series is convergent or not. In the modern era, if we know a series is convergent, if the series is convergent, then we can add the terms to some accuracy we need. To any accuracy we need, we can add the finitely many terms using a computer or calculator. So, mathematicians are interested in testing whether a series is convergent or not. So, there are many tests available for testing convergence of a series. We shall deal only two tests, root test and ratio test, and other tests are somewhat particular cases of this root test and ratio test. They are reduced from these things. Anyhow, what is root test? If sigma an is a series, we find alpha equal to limit supremum of n tends to infinity, nth root of mod an. So the term an may be positive or negative. We compute the absolute value of an, find the nth root. So for every n, we have a number. We have a sequence of numbers. The term is nth root of mod an. We find the limit supremum of that number. Suppose that limit supremum exists. For any sequence, limit supremum exists. It is minus infinity to infinity or any finite real number, limit supremum exists. Here all terms are non-negative, therefore the limit supremum lies between 0 and infinity. Anyhow, limit supremum exists. If that limit supremum is less than 1, then we say the series converges. If the limit supremum is greater than 1, the series diverges. And the test gives no, this is the very important part, the test gives no information if alpha equal to 1. If the limit supremum is equal to 1, we cannot get the information that whether it converges or diverges from the test. This is root test. The ratio test is somewhat different. For a sequence series sigma an, compute limit supremum of modulus of an plus 1 by an. If it is less than 1, then the series converges. Don't be in a hurry to say that if it is greater than 1, it diverges. It is not so. If sigma an diverges, if there is a stage after which mod an plus 1 by an is greater than 1, greater than or equal to 1 for all n greater than or equal to n naught. If I find a stage n naught such that after that stage all the terms are in modulus an plus 1 by an is greater than or equal to 1, then we can say the series diverges. This is ratio test. But among these two tests, root test is somewhat stronger than ratio test. What do we mean by stronger than? Means for any sequence of positive numbers, we can prove that limit supremum of this is less than or equal to limit supremum of this one. So, suppose this limit supremum exists and say some r, then immediately this limit supremum also exists, that is less than r. Since this limit supremum is less than 1, suppose some series, we know that the series converges using ratio test. I can find that, I can say that the series is a convergent series using ratio test. That means what? I find this supremum of limit supremum an plus 1 by an, and I found that this is less than 1. So since this is less than 1, that is, this is less than a sequence of positive terms I am considering. So this is less than 1 means this is also less than 1. Therefore, by ratio test, the series converges. So if somebody proved that a series converges using ratio test, then the series will be convergent using, we can prove that the series converges using root test also. But there are some sequences for which the convergence may be proved using root test, whereas we cannot prove the convergence using ratio test. For example, you consider this sequence. What is that is 1 by 2 plus 1 plus 1 by 2 cube plus 1 by 2 square, 1 by 2 power 5, 1 by 2 power 4, etc. I think you can follow the series. Nth root of, what is nth root of an? Nth root of an is the first root of this is 1 by 2, the square root of 1 is 1, the cube root of 1 by 2 is 1 by 2, fourth root of, 1 by 2, fourth root of 1 by 2 square, this is 1 by 2 power 2 by 4 I have done, and fifth root of 1 by 2 power 5, this is 1 by 2, seventh root of 1 by 2, 1 by 2, the ninth root of 1 by 2 power 9, 1 by 2 power 9, etc. For this even power, we get 1 by 2 power 2 by 4, 1 by 2 power 4 by 6, 1 by 2 power 6 by 8, and so on. So, what is the limit supremum of these things? Limit supremum of these things, there are only two major subsequences, the even term sequence, odd term sequence. This sequence, that is the odd term sequence, clearly converges to 1 by 2. The even term sequence also, if you look at that power, this is 2 by 4, 4 by 6, 8 by 10, etc. Then this terms, that is in the denominator, if I have 2n, then the numerator 2n minus 2, and therefore that sequence tends to 1. In other words, 1 by 2 power 2 by 4, 1 by 4 power 1 by 2 power 4 by 6, 1 by 2 power 6 by 8, etc. That also tends to 1 by 2. In other words, we can prove that the sequence nth root of an tends to 1 by 2, and therefore limit supremum is same as the limit of this, that is same as 1 by 2. But if I consider Cn plus 1 by Cn, I have written an plus 1 by an, I assume the sequence is an. The 1 by 2 by, 1 by 1 by 2. 1 by 1 by 2 is 2. 1 by 2 cube by 1. 1 by 2 cube by 1 is 1 by 8. 1 by 2 square by 1 by 2 cube. It's 1 by 2 square divided by 1 by 2 cube. In other words, 2 cube by 2 square, 2 cube by 2. 1 by 2 square by 1 by 2, yes. 1 by 2 square by 1 by 2 cube is 1 by 8. This is 1 by 8. 2, 1 by 8, 2, 1 by 8, 2, 1 by 8, etc. And therefore, an by plus 1 by an is this sequence. The limit supremum is 2. What about our ratio test? There are many terms. Right. This. Can we apply ratio test? What is ratio test? Ratio test is mod an plus 1 by an is less than 1. The limit supremum is 2. Therefore, the series doesn't, the test, ratio test doesn't say that it is convergent. It won't say the series converges. It doesn't mean that the series diverges. For divergence, some other property, that after some stage, all the an by an must be greater than or equal to 1. This is not so in our case. The an by an plus 1 becomes 2, 1 by 8, 2, 1 by 8, 2, 1 by 8. So many terms are greater than 1 and many an plus 1 by an are less than 1, and therefore the test give no information, the ratio test give no information about the convergence of this, whereas the root test says that the series is convergent. So in that sense, root test is stronger than the ratio test. Okay. Power series. For power series, if I consider, I am going to consider the complex numbers. You consider this series. What is Z? Z is any complex number. Any series of this form is called a power series. Z is a variable. If I put a particular value for Z, then we get a sequence of real sequence or a complex sequence. The terms A0, A1, A2, etc. may be anything. Anyhow, this is an example of a power series. These are examples of power series. Okay. Series of the form an z minus something power n, z minus z naught power n is also called a power series. Okay. What is the use of power series? If I know yes, power series sigma an z power n converges for z equal to say 17, then I can immediately say that the series converges for any number less than 17. For example, 16.29209. If I put z equal to 17, the series converges. Sigma n z power n converges. That means for this z and for this z also the series converges. This is a very important property of power series. In fact, for every power series, there is a circle such that the series converges for all numbers inside the circle. The series diverges for all numbers outside the circle, and on the circle, the series may converge or it may diverge depending upon the series, depending upon the coefficients A. Such a circle one can find for any power series. And that circle is called circle of convergence, radius is called radius of convergence, and center is called center of convergence. For z an z power n, the center of convergence is 0. For this series, this power series, an z minus z naught power n, z naught is the center of convergence. Okay. But how to find that circle? How to find the radius? The radius is given by this formula: 1 by limit supremum nth root of mod an. Even if the complex number mod an becomes a real number. Therefore, we can talk about nth root of mod an. We find the limit supremum. The limit supremum may be 0, it may be infinity. If the limit supremum is infinity, then R is 0. That is the point only we get as the circle of convergence. If limit supremum is 0, then R is 1 by 0. 1 by 0 I will take as infinity, and therefore R becomes infinity. That is the entire complex plane, the series converges. Okay. This is a list of some series, power series, for which the radius of convergence is given. Z power n by n factorial sigma. This is e power z. E power z is meaningful for any complex number. Therefore, R is this one. If we compute for z power n factorial, R is some copy paste mistake. For this n power n, z power n, R is 0. That is, only when z equal to 0, the series converges. For all other, the series diverge. And z power n equal to R, for n equal to 0 to infinity, z power n, if I consider this one, diverges at all points on the circle of convergence. Inside the R is 1, that is the unit circle. We have seen this one in terms of x power n. We have not usually x is real number, etc. there. Anyhow, for this, all points on the circle, for all points on the circle of convergence, the series diverges. For this sequence, this series, the series diverges if z equal to 1, and it converges for all other points on the circle. For z power n by n square, again the radius of convergence is 1 on the unit circle. On the unit circle, at all points on the circle, the series converges. So on. It's worthwhile to mention two terms: uniform convergence and term by term convergence. And we are not going to differentiate, etc. Anyhow, see, for example, you consider this one. This function is given, every power series is differentiable inside the circle of convergence, and the derivative can be obtained by term. That can be proved, but it's beyond the scope of this talk. See, for example, you differentiate this one. If we differentiate this one, this term z power n by n factorial, then this becomes z power n minus 1, n into z power n minus 1 by n factorial. That n will get cancelled. So z power n minus 1 by n minus 1 factorial. Again, we get the same series. In other words, we have proved that when we differentiate e power z, then we also get the e power z as the derivative. If we have almost all results we have proved are for sequence of non-negative terms. Now, this is what about the convergence of this series? Neither the root test nor the ratio test is helpful here. So there is a theorem. If C1, C2, etc., the modulus value decreases to 0, that is 1, 1 by 2, 1 by 3, etc., that decreases to 0. And one term is positive, other term is negative, positive, negative, positive. If the terms are like this, that is one term is less than or equal to 0, another term is greater than or equal to 0, then, and if the limit is 0, then the series sigma Cn converges. Using this theorem, we say that 1 minus 1 by 2 plus 1 by 3 plus 1 minus 1 by 4, etc. Another concept is absolutely convergence. If sigma an is a given series, if I am able to prove that sigma mod an is also convergent, then we say that the sigma an converges absolutely. Proved in suppose sigma an converges, but not this diverges, then the series is said to converge non-absolutely. It's I hesitate to use this term. Let us say the series converges but not absolutely. For example, this 1 minus 1 by 2 plus 1 by 3, etc., we have proved that this is a convergent series, and the modulus term is 1 plus 1 by 2 plus 1 by 3 plus 1 by 4, etc. This is a divergent series. So this is this converges, but not absolutely. Okay. Another important concept in terms of series is rearrangement of series. What do you mean by rearrangement? Something like commutativity. If I change this 1 by 2 and 1, just swap 1 by 2 and 1 only, then the value will not change. Can I swap infinitely many terms like that? That is, for example, I write 1 first, and then 1 by 2 square, and then 1 by 2. 1 by 2 power 4. I write 1 by 2 power 4. Let me call this as 1 by 2 power 0. First 2 even powers, and then 1 odd power. 2 even powers, 1 odd power. 2 even powers, 1 odd power. If I write like this, I may call this as a series rearranged from this. The series, this is a rearrangement of this series. Okay. Okay. See, for example, in general, if A0 plus A1 plus A2 plus etc. is a series, and I write A0 plus A4 plus A6, in some way I swapped the suffixes. So this is a rearrangement of this sequence, in this series. The main question is, say for example, if I write the suffix 0, 2, 1, etc. here, this is a sequence of natural numbers or non-negative numbers, so that each term comes only once. I take this as K0, K1, K2, Kk, etc. Then A K0, A K1, A K2, A K3, etc. having a plus sign between them is called a rearrangement of the series A0, A1, A2, etc. That is the definition for rearrangement. That is A K0, K1, A2. It's called a rearrangement of the series A0. Okay, an important question is, I have a series, convergent series. If I rearrange these terms, what do we get? Can I say the rearranged series also converges? The answer is no. If all the terms are positive terms, then the series, if sigma in converge, then all rearrangements also converge for the same unit. But when we involve negative terms also, this is not possible. The series may converge and its rearranged series may not converge, or it may converge to some other limit, and so on. So that is given by this theorem. This theorem is called Raymond's theorem on rearrangement of series. That is, I take a series sigma an. It is known that the series is convergent and it is not convergent absolutely. In that case, I can rearrange the series so that the partial sum sequence of the rearranged series for any given alpha and beta. Suppose some alpha and beta is given, they both may be minus infinity, both may be plus infinity, or anything. They may be equal. Anyhow, alpha is less than or equal to beta in the extended real number system. Then we can rearrange the given series. That is, the series must be convergent but not absolutely convergent. If such a series is given, and if I take alpha and beta like this, then we can rearrange the series so that for the rearranged series, the partial sum sequence has limit infimum as alpha and the limit supremum as beta. We can rearrange it like this. This is the famous theorem by Rowling. We can prove this in 2 or 3 minutes. Proof is simple, but in the book it may be lengthy, but the proof is simple. See, for a while you assume that in your mind, take the series 1 minus 1 by 2 plus 1 by 3 minus 1 by 4 plus 1 by 5. Odd terms are positive and even terms are negative. You take that series in your mind and we can easily follow. Pn, you construct 2 sequences. subsequences P1, Pn and Qn. The subsequences are Pn is the subsequence of positive terms. Qn are the subsequences of the absolute values of the negative terms. See, for example, for our series, Pn is the sequence Pn is 1, 1 by 3, 1 by 5, 1 by 7, etc. Qn is 1 by 2, not minus 1 by 2, 1 by 2, 1 by 4, 1 by 6, 1 by 8, etc. So, these are the two such things. For the alpha, given alpha and beta, satisfying alpha less than or equal to beta, take two sequences, alpha n and beta n, alpha n converging to alpha, beta n converging to beta. For technical reason, beta 1 is assumed to be greater than 0 and alpha n is less than beta n. Since alpha is less than or equal to beta, we can choose this alpha n less than beta n, we can choose such sequences. Okay. Now I am going to construct a new sequence. Sorry, I am going to rearrange the series. How I rearrange? I write the first positive terms. That is, in our series, I write 1 plus 1 by 3 plus 1 by 5 plus etc. How many terms I am going to write? These terms, we know our series 1 plus 1 by 2 plus 1 by 3 plus etc. That diverges to infinity. Now, before that, one fact has to be established. Sigma, after constructing Pn and Qn, consider the series sigma Pn and sigma Qn. We can prove that both sigma Pn and sigma Qn will diverge. So, the positive term series, if you erase all negative terms, what you get is sigma Pn. That sigma Pn diverges to infinity. Similarly, sigma Qn diverges to infinity. So in that case, after taking alpha n and beta n, I write P1 plus P2 plus P3 plus P4, etc. Up to I cross beta 1. Just after crossing beta 1, that since this P1 plus P2 plus etc. that goes to infinity, definitely at a stage we will cross beta 1. Even that may be the first term or it may be the 100th term, whatever it may be. Definitely at a finite stage we will cross beta 1. After crossing beta 1, go on writing the negative terms. Up to what? Up to you go below alpha 1 and then write down positive terms. Up to what? After just crossing beta 2 and then write the negative terms from the place where you stop. Qk plus k1, you stop at qk1, you will write k1 plus 1, etc. So it comes down, it is decreasing. Up to what? Up to it cross alpha 2. And again you write PM2 plus 1, PM2 plus 2, and up to you cross. Write the negative terms up to you, come down. Write in this way the real limit, the partials of have limit infimum as alpha. That can be proved. I think time for us to start. If you have any doubt, you please. I will try to answer it if my time permits.
1 minute. Thank you, sir. Yes, sir. There are 1 or 2 questions in the chat. Take in the afternoon, sir.
If you
read out the query, sir. Sivaram, what are the uses of in real life or in
this can be answered. We may not have any computation or not. It's not only for root list and red. Question asked by many people. There are two things. One is binary number system. Even we are using. You are in Vijayawada or some other place. I don't know. I am at. But we are talking through internet and so on. So we are computer, every E system. But when the misdeveloped, it's very long ago, hundreds of system was developed. We have 10 fingers. We have a lot of theory in base 10. Why do number system? But subject development, subject interest. Again, on the other hand, new concept, something, there is a driver. I want to run the vehicle without a driver. So I have to get a model. Developing theory is theory after generalization, good theories. If these two, okay, let us come back to our root test. See, for example, you consider your series n. If you add, say, for example, some 10 power 100 terms A, and after that, the number that 10 power 100 plus 1 less. Do you follow? The term 100 or 10, that is point not 100 zeros. This number has it's nothing but 0. If we are also to assume that without testing whether the series converges some mathematics, I am adding using a computer, and what I get, I assume that sigma, my computer program gave me a number. I add terms less than 10 power minus 5. It's an all terms, without all terms less than 1 by 10 power. All terms, point not 1. I leave all these terms. But as sigma 1 by n, I make. So I have to. After testing that, after knowing that the series is, use computer to the series up to some place. So, what mathematics? We want to find whether a given series is convergent. We can add some more like that for our purpose to find what is. We need sin theta, cos theta, everything. 21 to compute sin to the and find that for sin there is a series. Sin x is equal. We have a series. So that value to find Fourier series or anything many times. But if I add f, may be helpful for, but without or not, we cannot approximate using a computer. Or so, first of all, we must know not before applying that. So, two important tests available in analysis. Many tests are available in any undergraduate book. There are you can have many. This is a question. My gate professor Karnagaran said, an hour. I get pressure seeing this one. Why do you climb up a flight or helicopter and see what is there in Everest? Nothing is there. I climbed there is my climb up to Everest. There are many, a lot to climb up up to Everest. Even a small one, you climb up. After achieving that, there's a play called Jallikattu. Fight with we get some pleasure for that pleasure, and similarly there are applications. Day by day we need to create some model for analysis. Find the situation and take it. It is continuous or not. He convolve it. He do some. If it is an algebraist and define a binary operation, find an algebraic structure there. Try to find the object adjacency as the relation. He have more. Whatever the subject we know, we have to make the real life situation into that model. For analysis people, the model is, any model is maybe the set of people or anything, and we need continuous functions, differential functions. These are associate the real life problem into continuous functions, differential functions, integral functions. The integral value will be something like that. For algebraists, algebraic structures. For graph theorists, graph theorists. So to create such models, we need analysis. So in analysis, after creating a series or sequence, we want to verify whether it converges or not. In any other, it's, hello.
So that's all for today's session, sir. No other queries?
In the afternoon, by 2
By 2 we'll start the session, sir.
Okay, thank you, madam.
Thank you, sir. I request the participants to join by 2 o'clock. Sharp. Thank you.
One more gentle reminder to the participants. Those who want to use the Google Meet link, it is the same in the. Those are using the YouTube link, WhatsApp group. And for those who are not in the WhatsApp group, we'll send it to your mail. Do not worry. For Google Meet link, it is the same. Afternoon tomorrow and day after tomorrow afternoon also. Sir's session in the afternoon is from 2 to 3. Then from there on, Dr. R.Roopkumar, Head Professor, Department of Mathematics, Central University of Tamil Nadu will take over. So any questions you can ask, sir, regarding sequences and series in the afternoon also. That is what. Thank you, everyone. Thank you.
நான் அந்த பாத்ரூமாலதான் நிக்கணும், அடுப்பங்கால நிக்கணும். விட்டுலாம்ல, உனக்கு என்ன அவசரம் நாளைக்கு அவசியம்